conference. And it's very nice to have Silke Rolles now, because we heard all the family. We heard the baby speaking already, and we heard, I think, the father, so now we hear the mother. She'll speak about edge-reinforced random walk on a two-dimensional.
Yeah, so thank you for the introduction, and I'd like to thank the organizers for inviting me and giving me the opportunity to speak here. I'll talk about joint work with Franz Merkel and the model we've heard already about in Tom's talk at the beginning of the conference, and Franz has introduced it. But since this is already a few days ago, I want to go through the model definition again. So we consider linearly edge-reinforced random walk. That's defined on a locally finite connected graph with a finite or countably infinite set of vertices V and a set of undirected edges E. And on this graph we consider a nearest neighbor random walk. So it's a process xt. T runs through the discrete time set n0. We start at time 0 in one distinguished vertex, which I'm going to call 0. And it's a nearest neighbor walk, so between two time steps we just traverse one particular edge. It's a random walk with memory, and the memory is encoded in edge weights which depend on time. So WE of t is the weight of the undirected edge E at time t. And sometimes we also speak of the vertex weight WV of t, which is just the sum of the weights of the edges incident to V. And we start initially for this talk with constant initial weights. You could start with space-dependent weights. That's what Franz did on a finite graph, but for the results we look at here, it's convenient to have constant weights. And the reinforcement scheme is linear edge reinforcement. So you have your reinforced random walk, it starts in the vertex. Then, well, whenever an edge is traversed, the weight of that particular edge is increased by 1. And the weight of all other edges don't change in that time step. And the transition law is what you expect. So given the history up to time t, well, if you're here at time t plus 1, you're going to be at the nearest neighbor point, and you jump with probability proportional to the weight of the edge at that particular time. So that's the model. And yeah, we heard already a bit of history. The model was introduced more than 20 years ago by Percy Diaconis. And already pretty soon after the model was introduced, Diaconis asked about recurrence transients behavior of these walks on ZD.
Do you know what the motivation was for why he introduced it? Or
why he introduced it? Well, he says he was walking through Paris and walking through the streets and observing that he would return, that he would traverse again and again the same streets, and so he made up a model for that. Okay, and okay. That's this one.
I guess that's as good an answer we're going to get. That's fine.
Yeah, I think he told me this story at some point. So
it wasn't for any deep physical reason except for wondering about Paris.
Yeah, so I don't know about any physical motivation for it.
I think it's just a generalization of the standard urban model which you introduce in typically positive probability. As an example, I think that is what probably the motivation. If you look at
it is a learn-like model.
if you
neural networks.
I don't know. I don't know. Okay, so one basic question is really, I mean, do you have recurrence? Do you have transients? Recurrence meaning, does the random walk return to the origin infinitely often with probability 1? that's something we know very well for simple random walk, where you know that you have this recurrence in dimensions 1 and 2, but not in higher dimensions. So you would want to answer that question, yeah, say for constant initial weights or for initial weights equal to 1. And I mean, okay, you would expect that in 2 dimension the process is recurrent, because I mean it should return more easily than the simple random walk. And it's in fact a simple argument to see that on any graph the edge-reinforced random walk has to visit infinitely many points, so you cannot really get stuck. So unfortunately this problem is still open. And I should also say, so recurrence is also equivalent to visit every vertex infinitely often with probability 1, or also to return at least once to the starting point with probability 1. This is an equivalence we know for Markov processes. This is not a Markov process, but it's a mixture of irreducible Markov chains, and out of this you can get this equivalence. So here's a simulation that Franz Merkel did, and it's this reinforced random walk on 100 times 100 box with periodic boundary conditions, and the starting point is in the middle of the box. And what you see here, well, the process was run up to time 1 billion with initial weights all equal to 1. And what's drawn is the weight at the vertices at time 1 billion. So it's, what is it? It's not quite the local time, but something like the local time. And you have the color code for how often, for how big these weights are, where red is, the dark red is the maximum, and the black is the minimum. And okay, you can see here that you have some small dark red islands, so small islands that have been visited really a lot of times, and they are not really very close to the starting point necessarily. And that also shows already some difficulties in the model. The process may just go somewhere and then spend a lot of time there.
That's the red is really much more than the green or the
Yes.
the light green. So we're talking about really orders of magnitude.
Yes.
Was there another simulation for other values of A or not?
Okay, you did some, but I don't remember what they looked like. Franz, can you? What did they were similar probably.
I was actually interested in smaller values of A.
If you have smaller values of A, then you have stronger reinforcement, yes. So, you want to say something, Franz? No, okay. Good. So just a tiny little bit of history. So I've told you that on ZD already the simple question is open. The situation is much easier if you look at graphs without cycles, meaning trees, because then there is a simple argument that shows you that the process has the same distribution as a random walk in an independent random environment. So that's the model that Ofer talked about, except that here you have it on a tree, and then it's easier to analyze, and you can give an explicit description of the random environment in terms of Dirichlet distributions. And that was used already very early, so by P. Mantle in '88, to show that on a binary tree there is a phase transition between recurrence and transience. So he could show there is so you consider the process on a binary tree with constant initial weights, A, and then there is an A critical such that for A smaller A critical you have a mixture of positively recurrent Markov chains, and for A larger you have a mixture of transient random walks, of transient Markov chains. Okay.
As you may know, that's analogous to what we have in localization. So we know on a binary tree or tree that there is localization for certain strengths of disorder and not for others. So
I see. Okay. So, yeah, for graphs with cycles, the situation is more difficult, and here just one slide about a series of papers about some one-dimensional graphs with cycles. So we could prove together with Franz that this model, the linearly edge-reinforced random walk with constant initial weights, is recurrent, so returns to the starting point infinitely often with probability 1 on the following graphs. So the first paper was just about the simple ladder, so you take just a strip of width 1 from the two-dimensional lattice. Well, first we proved it for large initial weights for some technical reasons. Later we generalized it to any positive initial weights. Then we could show it for z times some finite graph, and finally for a whole class of one-dimensional graphs being periodic with some reflection symmetry. And I'll say later a bit more about this symmetry we need. So for the remainder of the talk, I want to show you a result about one two-dimensional graph or class of two-dimensional graphs where we can prove something. And I apologize to those who have heard this talk already. So we look at the graph GK, which is obtained from the two-dimensional Euclidean lattice by replacing every edge by k edges in series. And here I've drawn G4, but unfortunately we can't prove anything about G4, but we need GK with large K. And so what we can show is that if you take K large enough, meaning larger or equal than 130, and the A small, meaning so A is the initial weight, it should be strictly positive, but less than the K minus 129 over 256, then the edge-reinforced random walk on GK with these constant initial weights starting in 0 is indeed recurrent. Okay.
These numbers are optimal, or
No,
just because
no.
that's what you can prove?
No, this is what we can prove. I mean, so yeah, I don't know, what do we expect? I mean, I would expect that on Z2, so if you have K larger or equal than 1 and A larger than 0, then you have the result. But I will kind of indicate that for technical reasons, the proof only works under these conditions. And so how do we prove this? Everything boils down to showing the following estimate for hitting probabilities. So for ZA, denote by tau sub A the hitting time of A, and by tau sub V the hitting time of a vertex V. Then under the hypothesis of the previous theorem, meaning if the K is large and the A is small, then we can show the following. If you take a vertex L of degree 4, which is far enough away from the starting point, then the probability to hit this point L before you return to the starting point is bounded by what? By a constant divided by the infinity norm of your point L to a power which is strictly larger than 1. And so the important thing is that you have a power which is 1 plus xi with a positive xi, because you would like to look at the hitting time of or the exit time from a large box centered around the origin. That's the boundary of VL. So what's the probability to hit the boundary of such a large box before returning to the starting point? Well, you can bound that just by saying this is bounded by the sum over these probabilities of hitting a point on the boundary, and just sum over all points on the boundary. There is a linear number of points on the boundary, so you take the first estimate and you get still something, yeah, you lose a power 1, so but you still have something which goes to 0 when the box size goes to infinity. And so from the second estimate, you know that the probability of never returning to your starting point 0, that this is 0, because this bound goes to 0. Okay, so
Do you believe this exponent c? I guess I asked you this before, but I still want to be. I mean, is it possible that that's a fast power law or even exponential?
I'm not sure whether it's exponential. I mean, it's exponential if you look at one-dimensional graphs.
Yes, it is exponential.
This we know. But okay, I mean, I guess I would expect. I mean, in
I like that.
okay, in 3 dimensions, I don't know anything.
So it is exponential in 1 dimension.
It's exponential
in strips.
In
for
strips,
example.
yeah.
Okay.
This it is.
Then
This it
I
is,
would kind of expect it here too. But that's only by analogy.
I don't
to
know.
what we would expect.
I don't know. I mean, the exponent would depend on the initial weight. And I think in 1 dimension you can say what the exponent, I mean, if you really have 1 dimension, namely the line, then you can say what the exponent is.
Sure, that's what we call the localization limit.
Yeah, but here,
And it
I
would
mean,
depend upon the A, the strength of the A, right?
yes, yes,
And the larger A gets, the worse that becomes, the worse it is.
yeah, yeah. So I'm pretty sure this is by no means optimal, but yeah, I don't know. I'm okay. Yeah, I should also say we have such a bound. I mean, yeah, for arbitrary k and a, but then we have an exponent which we don't get larger than 1 in the first line. So you can write down something for the first estimate, but then the second estimate gets useless, because then you have something which is larger than 1. So what? Okay. Yeah, just one word. So I present the result for this graph GK, for this 2-dimensional graph. The proof we've written is actually quite general, and we've worked out what's general. So it works really the same way for what we call k-diluted versions of a class of 2-dimensional graphs. What's a k-diluted version? You take a graph and just replace every edge by k edges in series. What you need is sufficiently many reflection symmetries, and I will come to that in the proof. You need, well, everything works if you have constant initial weights. You can also allow some periodicity. I mean, if this is compatible with the symmetries, and you need large k for our argument.
So you use the fact that you need to use that your A's don't have edge dependence, not just their.
Yeah, I mean, they could slightly depend on the edges if it's periodic and reflection
not otherwise.
No.
You wouldn't want to take random ones.
No. I mean, for this argument, I will show you there's one point where you really need a symmetry, and that's crucial. Okay, so we had this exponent 1 plus xi in this estimate, and we have explicit control of that. It's a function of k and a, where you have a c in the numerator, and the c has to be chosen between 0 and 1 in such a way that the quantity is strictly larger than 1. That's what we need in the proof, so that gives you our conditions on having k large and a small depending on k. Now, I want to go into the proofs. So first I want to remind you of the magic formula that you've seen, and here I just presented for a finite box of gk, I call that box gi, if I think of length ki times ki, and I need periodic boundary conditions to have enough symmetry. So the set of edge weights on this graph is the set omega I of all strictly positive edge weights. And given such an x, such a set of weights, I denote by qx the law of the Markovian random walk that starts in the point 0. That's our fixed starting point for all random walks we consider, and transitions are made with probability proportional to these fixed weights x. So it's just a Markovian random walk, the weights never change. On the other hand, I consider the edge reinforced random walk on gi with initial weights equal to the constant a, starting point 0 again. I denote that law by pi. And then we know that the edge reinforced random walk on this finite graph gi is a mixture of reversible Markov chains, meaning that there is a probability measure q0 on the set of weights such that the probability of any event A for your reinforced random walk can be written as the corresponding Markov chain probabilities qx of A, but you have to average with respect to q0. So Franz has shown you this result where the event A was just a finite path, so just x0 equals some v0, x1 equals some v1 up to xn equals some vn, and then you can write down the probability qx of A explicitly, but this is of course equivalent of having the laws of these two processes equal. And he has also indicated that the mixing measure q0 that's unique up to, you have some freedom by normalizing the weights x. If you multiply all of them with the same constant, that doesn't change anything. You can obtain the q0, we are here on the finite graph, so you can obtain the mixing measure just as a limit of the local time spent on the edges, suitably normalized.
This is really telling us that the q0 is giving us the distribution for the random walk in the random environment.
Yeah, the q0 is the random environment distribution.
Random environment, and then everything follows from understanding the random environment.
Yes, yes, right. And yeah, and so we've seen what the q0 looks like in Franz's talk. I will come to that again. But first let's go back to our goal. We want to prove this estimate that the probability of hitting a vertex L far away before returning is bounded by this power in the distance of L to the origin. And we do this by proving the two inequalities which I've shown here. So for any vertex, just denote by xv, the weight of that vertex in the fixed environment x, so it's just the sum of the xe e incident to v. And then, we compare these, we prove that this probability is bounded by the expectation with respect to the random environment of XL, so L is a vertex far away from the starting point, divided by X0, 0 is the starting point, to the power 1/4. And I should say, well, this first inequality, that's simple. That just follows from the fact that you have a mixture of reversible Markov chains. And from that, I mean, you could put here a different power smaller than 1. The reason we have 1/4 is that the second inequality, which is the hard inequality to prove, we can show only for this particular power 1/4. So I'm not going to tell you how to prove the first inequality because that's really simple and it doesn't depend on the model. I'm going to show you how to prove the second inequality. So just to summarize, to prove recurrence, all we need is really to bound this quantity of which is given in terms of the random environment. So that's what we want to look at, that's this inequality. And so there are some steps. First I want to recall you the magic formula. We need to use the explicit form of the random environment. Then we use some statistical mechanics reinterpretation of this, and we see that this expectation turns out to be a partition sum if we give it the right interpretation, and then we use a variational principle to bound it. So first we need to recall the magic formula from Franz's talk, and here it's slightly different. But it's the same thing. So, yeah, Franz gave you the measure Q0 in the following way. He said it has a density with respect to the Lebesgue measure on the simplex. So that was just normalizing the x's in such a way that they all sum to 1. Here it's convenient, since we consider these boxes which are growing, to take a different normalization. So you fix one edge, E0, incident to the starting point, and you want to normalize in such a way that that particular edge gets weight 1. Because of this, as a reference measure, it's convenient to take this measure rho, which gives the point mass to the weight of the edge E0, and on all other components it's just a Lebesgue measure with density 1/xe, which has the effect, if you do a scaling, if you multiply everything with c, this is invariant.
So it is, yes. So, but the xe's run from where? From 0 to infinity. 0 to infinity, and are they? But do you still have a simplex that they run over, or not?
No.
Simplex is gone.
So here the space is 0 infinity to the e. So I mean, it's more convenient to have this. Okay. So I want to give you the magic formula again. So as a notation, call dv the vertex degree of the vertex v. Ti is the set of spanning trees of G, so the set of maximal connected acyclic subgraphs of G. Ci is a normalizing constant. And then the random environment distribution has the following density with respect to rho. So it's given by a normalizing constant, which in principle we know, but we don't need the explicit form for the proof here. Then you have a product over all edges in your graph, xe to the initial weight a. Product over all vertices, weight of the vertex v to some power. The starting point 0 plays a special role, so it gets a square root of x0 extra, and then you have a sum over all spanning trees, product over all edges in the tree of xe. So that's the distribution of the random environment. And now we do some reinterpretation of this, so you can say, okay, this density looks like a Boltzmann-Gibbs density for some interacting system. And so here comes a crucial symmetry. Our starting point is 0 and it has vertex degree 4. So take a vertex L which also has vertex degree 4, and we consider, well, this random environment distribution for the box with periodic boundary conditions. So every vertex of degree 4 plays the same role, and that's also why the two normalizing constants for the densities with the two different starting points are the same. And because of this, the measures, the random environment distributions for the starting point 0 and L, they are absolutely continuous with precisely this Radon-Nikodym derivative. So it's just the square root of xl over x0. And I mean, this just pops out from this particular form. I mean, this is the only term, and the normalizing constant doesn't bother you because you have periodic boundary conditions. So then just call this e to the sigma. So sigma is a half times the log of xl over x0. And then interpolate between q0 and ql by this family p eta. So p eta is defined as e to the eta sigma, divided by a suitable normalizing constant that makes this a probability measure. And as a reference measure, you have the q0, so the random environment distribution for the starting point 0. And you let eta run from 0 to 1. Yes?
Yeah, so I'm just curious, because it looks like your reference measure rho also means something about where the origin, where this delta function is.
Yeah.
Why doesn't that show up here?
Okay, so the you mean with the e to the sigma, the normalizing doesn't.
No, the d rho depends upon where the
Yeah.
origin is. One edge to
Yeah. But the nice thing is that the normalizing constant doesn't depend on what the reference edge is, on how you normalize.
Okay.
So that's okay. That's a good point. That's also a point our referee pointed out.
I would make another remark if you go back to the previous slide. The formula, see the power A there.
Yeah.
For us, that plays the role of a beta, like an inverse temperature. So the larger
Yeah.
A is, for us, that means the lower our temperature is, and provided in more canonical form. The determinant there, which is the sum over spanning trees, doesn't have it, but the rest of it has a weight, which is like a temperature.
Yeah. Okay, so we look at this interpolating family, and so for eta equal to 0, you have the measure q0. For eta equal to 1, you have precisely the measure ql, because then your density is just the e to the sigma, and the ql is a probability measure. So you are interpolating between these. The z eta is just the partition sum. And so we can, we say that the log of the partition sum is the free energy. From this symmetry here, you get, in fact, also a symmetry here between the partition sums for eta and 1 minus eta. And in fact, the derivative with respect to eta of the free energy, that turns out to be the expectation of sigma with respect to the p eta, and that has this particular symmetry. And now the crucial thing is that if you look at this partition sum for eta equal to 1, then you have here e to the half sigma, so that's xl over x0 to the power 1/4, and you are taking the expectation with respect to the random environment. So that's precisely the quantity we want to estimate. So the key quantity we need to estimate is just a partition sum in this interpretation. And so the interpolating measures p eta, they are absolutely continuous with respect to the rho. You can write down what the density is. You just have the eta popping up here in the x0 and the xl powers. And how could you possibly think of this? So you could think of the p eta describing some kind of rubber membrane where, if here you have your vertices, and on the y-axis you have your log xv, you can think of applying a force 1 minus eta at the starting point and the force eta at L, and kind of thinking that the thing goes down as you move away from the starting point. And from the symmetry I had on the previous slide, you think that qualitatively the free energy should look like this.
How did you get that picture for the free energy?
So how did you get that? So you have, here you have a symmetry around a half.
Oh, yeah.
That should be the derivative of it. So it's, and the variance of sigma with respect to p eta is the second derivative. So it's a convex function.
Yeah, it's a convex function.
It's always a convex function, yeah. So just qualitatively it should be like this. Yeah, and you have probability measures at eta equals 0 to and 1, so at these values you have the value 0. Fine, so we should bound this free energy. And so what do? We use the variational principle. So you have the p eta as e to the eta sigma divided by z eta with respect to the reference measure q0. Now if you have a probability measure nu, just call u of nu the internal energy, so the expectation of sigma with respect to nu. Then denote by S nu p eta, just the relative entropy of nu with respect to p eta. And then you have the free energy as the internal energy plus 1 over eta times the relative entropy. And then the variational principle tells you that the free energy is minimized for the measure q0, which is our reference measure, and the minimum value is 1 over eta log z eta. So that's a standard variational principle. I mean, I have a proof here which is it's standard, and I guess for this audience I can probably skip this. So you have this variational principle, and how do you apply this? You need a suitable measure nu to get a reasonable bound. Namely, we take a class of measures pi depending on a real parameter gamma and on the eta, and we choose it in such a way that, one can think of the nu being close to the q0. For q0 you have the minimum, so you want to be close to it. we choose it in such a way that the internal energy of nu is given by the internal energy of p eta plus something linear in gamma, and the relative entropy of nu with respect to p eta is bounded by something quadratic in gamma divided by log L. And okay, we have explicit control of the constants.
So you already have one deformation parameter, but you're introducing another one?
Yeah, so you have the eta, which is this interpolation parameter, if you want, and now we introduce a gamma, which is a real, which can run over the whole real line. So that's the second parameter, and we will optimize over that.
What is this gamma? I don't understand.
So gamma is now a real number, and it can be any real number. And I'm just saying we want to choose. I have to show you that this is possible, but we want to take a nu such that the internal energy is given by this, and the entropy satisfies this bound for any real gamma. So in fact we take a whole class of measures nu, and then for the whole class we apply the variational principle, and then we optimize over gamma. But this will come, right? So we apply the variational principle. It tells us the free energy is minimized for the Q naught with this value, and we get an upper bound if we take the free energy of any other measure. So this was this equality holds for the free energy, and now I just insert these two conditions. So I have internal energy of p eta plus something linear in gamma plus a quadratic entropy bound, and this holds for any real gamma. And so now I take the gamma in R for which this quadratic function is minimal. So I optimize over gamma, and then I get this bound, and now comes the symmetry in, namely the internal energy of the p eta, namely the expectation of the sigma, which was the log, or a half times the log of xl over x0. That's 0 if you choose the eta equal to 1/2. And the reason, the reason being, again, this one symmetry between Q0 and QL that I had shown you on one of the previous slides. And that's, so you have this term precisely dropping out for the eta equal 1/2. And then, the good thing is you got rid of this term here in the upper bound, so you're just left with this one. And so then you have a bound for the partition sum at the half, and this gives you precisely the bound you want. I mean, keeping track of the constants, you get precisely what I told you. Okay, so I've shown you that you can interpret this key quantity as a partition sum and then bound it using the variational principle. So I should still give you an indication why we can choose such a family of measures nu satisfying the two conditions. So how do we choose these measures nu? Well, we choose it as image measures of the p eta under a suitable deformation map. Namely, you take the weights xe and you multiply them by e to the gamma phi e, where phi is roughly the Green's function of simple random walk on the lattice, appropriately truncated and scaled. Okay, so that's what you do. What's the effect of this? If you look at edges incident to the origin, then the phi will be 0, if you define it appropriately. So the weights of the edges incident to the starting point 0, they will not be changed under this deformation, whereas for edges incident to L, the phi will be equal to 1, so there the weights will be multiplied by e to the gamma. And, okay, and you should think that the optimal gamma is then a negative one, and so for negative gamma, this kind of models what you expect from the Q0, namely that the weights decay. And these transformations leave the rho invariant. So that's one property, and from that you get the condition for the internal energy, namely what happens to the sigma if you apply this deformation where you have half log xl over x0, and so this guy is multiplied by e to the gamma, this guy is unchanged, so in essence you have an additive constant of gamma over 2, and that gives you this this condition on the internal energy. So that's something easy. And for this you wouldn't have needed the particular form of the Green's function. And that comes in the entropy bound, which is the most delicate part. So we should show that this relative entropy of the deformed measure pi gamma with respect to the p eta is bounded by something quadratic in gamma. And how do you do that?
You have a play between the quadratic and the linear part, right?
Yeah, yes. Yes. So, yeah, you have to bound this function. So you integrate with respect to the image of p eta under the deformation map psi gamma. So you can write the g as an expectation with respect to p eta of this function, which you can actually write down explicitly using this magic formula. And what are properties of this G gamma? So it's a relative entropy, and as such it's non-negative. For gamma equal to 0, you don't deform at all, so you're stuck to the measure p eta, so G of 0 is 0. And it's not hard to see that you can differentiate the function g as often as you like, and as a non-negative differentiable function with value 0 at 0, also the first derivative must vanish at 0. So you can do this second order Taylor expansion and write it as an expectation with respect to the g double prime, and you obtain the expectation by just twice differentiating the f gamma, which you could write down explicitly. And the essence there is that the second derivative can be expressed as a difference of two variances. They just turn out to be two variances with respect to some complicated measures, one being a local one and the other one being a tree variance coming from this spanning tree term. And the nice thing is that this complicated one has a negative sign, so variances are non-negative, so you can drop it for the upper bound. So that's the nice thing. And maybe since I'm running out of time, so there is an explicit form for this local variance. It's just the sum over all vertices of some variance that only depends on quantities close to the vertices. On the other hand, there is a complicated tree variance that involves integration with respect to a more complicated measure, but that's the one we are dropping, and then, I mean, to get the entropy bound, you need to estimate this local variance. And so there comes in the explicit form of the Green's function phi. So you bound the local variance by this kind of Dirichlet form, and then you get where you want to get. That's the essence. And yeah, and so I've illustrated this for this two-dimensional graph. I mean, also our general proof for one-dimensional periodic graphs follows the same line of argument.
If I were to do strips, then you could do strips this way too.
Yeah, you could do strips this way too. Yeah, I mean, then I mean, you could. What would you do? You would use a linear phi. Then it gets easier, and then you get exponential bounds for the probabilities. Okay, thank you.
Yep. There were many comments. To the right. Are there any more comments? Do you want to make another comment?
Well, yeah. So this is, of course, reminiscent of what happens when you have symmetries in a system. You have this translation symmetry, and you're exploiting it by a word identity, and do it. You have internal symmetries or other things. So it's very reminiscent of what one does in Hermann Wagner or other systems.
With these comments, let's